Today, we're doing something a little different. We are attempting a mathematical heist. Our target? An equation that looks so complicated, so messy, that it was basically considered impossible to solve with perfect accuracy. We're going to crack it, step by step.
So here's our plan. First, we'll size up the target, this so-called impossible equation. Then, we'll look at the old tools and why they just won't cut it. After that, we find our secret key. Then the real fun begins. We crack the combination, reveal the treasure inside, and talk about why this whole thing might just rewrite some of the rules.
All right, first up, let's meet our target. Think of it like a high-security vault, but instead of steel, it's made of an 18th degree polynomial.
I mean, just look at this thing. It's an absolute monster. An 18th degree polynomial, which is wild enough. But look at its coefficients. They're huge. The challenge here is to find the exact value of x that makes this whole long mess equal to 0. And for a very long time, finding that with perfect precision wasn't just seen as hard, it was thought to be pretty much impossible.
So how would you even begin to tackle a beast like this? Well, let's take a look at the traditional tools of the trade, and you'll see pretty quickly why they're not the right fit for this job.
So, on one side, you've got your standard numerical methods. And hey, they're great for a lot of things, but they only give you an approximation. They can get you really close to the right answer, but it's never going to be perfect. And for our heist, close enough is not good enough. We want the exact treasure. But, on the other hand, there's this new approach, Ezouidi's theorem, that promises something totally different. An exact, precise solution. No rounding errors, no guessing, just certainty.
Now, every great heist needs a unique tool, right? A master key that can open a lock that everyone else thinks is unpickable. For us, that key is a really clever piece of math called Ezouidi's theorem.
This is our secret weapon. Now, I know it might look a little intimidating, but just think of this formula as our codebreaker. It's specifically designed to take a huge, complicated polynomial and just systematically break it down piece by piece, searching for a hidden pattern. You can think of this formula as having 4 main jobs. One part of it balances all the terms, kind of like a scale. Another part acts like a ladder, letting us step up and down through all the different degrees of the polynomial. A third part is what actually pulls in the numbers from our target equation. And then there's the most important part, the recursive engine, which makes sure every step we take builds on the last one, creating a direct path to the solution. So, our plan of attack has 3 very clear steps. First, we're going to rewrite our polynomial using some new symbolic language. Second, we'll use our master key, that formula, to calculate these new coefficients one by one. And third, if all goes to plan, the results from step 2 will lead us straight to the exact answer. It's a clean, methodical path right through the vault's defenses. All right, planning's over. Time to get to work. We are now officially applying the theorem and cracking the combination.
We start with the first step, where k equals 1. We plug all those big numbers from our polynomial into the formula, it does its thing, and out pops the answer, 0. It's like the first tumbler in the lock just clicked into place. Interesting.
Okay, now for the second tumbler. We run the formula again, this time for k equals 2, and the result is 0. Again. Okay, wait a minute. Something's going on here. We've got a pattern. We go for the third step and click. Another 0. The pattern is absolutely undeniable at this point. So let's speed this up. Each time we run one of these incredibly complex calculations, the formula just chews it up and spits out the same simple answer. We go through step 7, step 8, 9, all the way past step 10, and the answer is just relentlessly the same. 0, 0, 0. It's amazing. And now for the grand finale, the final step, k equals 18. This is the most complicated calculation of them all. We run the formula one last time, and what do we get? 0. The pattern held all the way to the end. The lock is open. So here it is, the big payoff. Every single one of those new symbolic coefficients we calculated, from the very first one to the very last, they all simplified perfectly to 0. It turns out all of that insane complexity on the surface was just hiding this beautiful underlying simplicity.
We've cracked the code. The vault door is swinging wide open. Let's finally see what treasure was hidden inside all that math. And here is the big reveal.
Because all of those coefficients turned out to be 0, our original monster of a polynomial, with all its bells and whistles, it just collapses. It transforms into this. P of x equals x to the power of 18 equals 0. It's just breathtakingly simple.
And from there, well, the solution is staring us right in the face. If x to the power of 18 is 0, then x has to be 0. That's it. That is the one exact perfect solution that was buried deep inside all of that complexity. Our heist was a complete success.
But you might be wondering, hang on, what about the 18? Doesn't an 18th degree polynomial need to have 18 roots? And you'd be right. This brings us to a cool concept called root multiplicity. It just means that in this very special case, all 18 of the roots happen to be the exact same number, 0. So the solution is x equals 0 with a multiplicity of 18.
So we solved one very specific, very unique-looking equation. You might be thinking, why is this more than just a neat math trick? Well, let's zoom out for a second and see why this actually matters in the bigger picture.
You see, for over a century, a famous idea in algebra called Abel's impossibility theorem has basically said you can't create a simple, exact formula to solve general polynomials if they're degree 5 or higher. Now, this new method doesn't exactly break that theorem, but it kind of finds a secret back door. It shows that some of these so-called unsolvable polynomials might not be so unsolvable after all.
And that leaves us with a really fascinating thought to end on. This whole thing was a heist on a single problem, sure, but it shows that the right key can open a lock that everyone else thought was unbreakable. It really makes you wonder, what other impossible problems are out there, in math or in science, just waiting for someone to discover the right key? What other rules are just waiting to be rewritten?